Let me tell you something about time that's going to bother you. It bothered me for years, and I think it should bother anyone who really thinks about it. You see, we all walk around acting like we understand time. We look at our watches, we make appointments, we remember yesterday, and we plan for tomorrow. But here's the thing. Nobody really knows what time is. I mean, we use it every day, but when you actually try to nail down what's happening, it gets slippery. And I'm going to explain to you why everything you think you know about time is probably wrong. Now, I want you to think about something very simple. You drop an egg, it hits the floor, and it breaks. Splat. Yolk everywhere, shell in pieces. You've seen this 1,000 times. But here's my question for you. Have you ever seen an egg unbreak? Have you ever watched the yolk flow back together, the shell pieces fly up and reassemble themselves, and the whole thing jump back into your hand? Of course not. Nobody has ever seen that. But why not? The thing is, the laws of physics don't care which direction time goes. If you take Newton's laws, or Maxwell's equations, or even quantum mechanics, and you run the movie backwards, everything still works. Every equation, every law we've discovered about the fundamental behavior of particles, they all work perfectly fine whether time runs forward or backward. So why does the egg only break in one direction? Why does time seem to have an arrow pointing in just one way? This is one of the deepest problems in all of physics, and I'm going to take you through it the way I figured it out myself. It took me a long time, and I made a lot of wrong turns, but when you finally see the answer, it's beautiful, and also terrifying, because it means something very strange about the universe we live in. Let me start with what's called the second law of thermodynamics. Now, don't let the fancy name scare you. It's very simple, really. The second law says that in any isolated system, disorder tends to increase over time. We call this disorder entropy. Think of it like this. If you have a box with a divider in the middle, and on one side you put all the red balls and on the other side all the blue balls, that's organized. Low entropy. Now remove the divider and shake the box. Pretty soon the red and blue balls are all mixed up together. That's high entropy. And here's the key thing. You never see them spontaneously unmix. You can shake that box forever, and the balls will never separate themselves back into red on one side and blue on the other. Why not? This is where it gets interesting. You see, there's nothing in the laws of motion that forbids it. Each ball bouncing off another ball obeys Newton's laws perfectly. If you could somehow reverse all the velocities of all the balls at exactly the same moment, they would retrace their paths and end up separated again. The laws don't care, so what's going on? The answer is probability, pure, cold, mathematical probability. There are vastly more ways for the balls to be mixed up than to be separated. When I say vastly, I mean a number so big it makes the number of atoms in the universe look like nothing. So if the balls are just randomly bouncing around, the overwhelming likelihood is that they'll be found in a mixed configuration simply because there are so many more of those configurations available. It's not that unmixing is forbidden. It's just so incredibly unlikely that you'd have to wait longer than the age of the universe to see it happen. Now, here's where time comes in. The reason the egg breaks and doesn't unbreak, the reason the balls mix and don't unmix, the reason cream spreads in your coffee and doesn't unspread is all the same. We're moving from low entropy states to high entropy states, and that's what defines the direction of time. The arrow of time is the arrow of increasing entropy. But wait a minute. I said the fundamental laws don't care about direction, so where does this arrow come from? This is the part that kept me up at night. If you take any physical process and run it backwards, the microscopic physics works perfectly, but the macroscopic behavior is completely different. A movie of an egg breaking looks normal. The same movie played backwards looks absurd, impossible. How can the small-scale physics be time-symmetric while the large-scale physics is not? The answer, and this is really quite remarkable, is that the arrow of time comes from the initial conditions of the universe, not from the laws themselves. At the beginning, at the Big Bang, the universe was in an extraordinarily low entropy state. Everything was smooth, organized, packed together in a very special configuration. And ever since then, entropy has been increasing. We're all just riding this wave of increasing disorder from the beginning of time. You see, the laws of physics are like the rules of a game. They tell you what moves are allowed, but they don't tell you how the game started. The reason time has a direction is because the game started in a very particular way, in a very special, low entropy configuration. If the universe had started in a high entropy state, all mixed up and disordered, there would be no arrow of time. Nothing interesting would happen. No eggs would break because no eggs would form in the first place. No stars, no planets, no people. Now, let me tell you about a different way to think about time, because this is where it gets really strange. So far, I've been talking about the thermodynamic arrow of time, the one connected to entropy, but Einstein showed us something very different about time when he developed relativity. In relativity, time is not separate from space. They're woven together into something called space-time. And here's the weird part. Different observers can disagree about what happens simultaneously. If I'm standing still and you're flying past me at high speed, we will not agree on whether two distant events happened at the same time. We'll each have our own notion of now that depends on how we're moving. Even stranger, in relativity, there's no universal now. There's no cosmic clock that everyone agrees on. Time is relative. Your clock and my clock tick at different rates, depending on our relative motion and our positions in gravitational fields. This has been measured, by the way. GPS satellites have to account for relativistic time differences, or your navigation system would be off by miles. So now we have two very different pictures of time. In thermodynamics, time has a direction, from low entropy to high entropy. In relativity, time is a dimension, like space, and different observers slice it up differently. How do these fit together? This is still an open question, honestly, but here's what I think is happening. The relativistic picture tells us about the structure of space-time, how clocks and rulers behave. The thermodynamic picture tells us about the content of space-time, about how matter and energy evolve. The arrow of time is not built into the fabric of space-time itself. It emerges from the way matter is organized within that fabric. Think of it this way. Space-time is like a blank canvas. The laws of physics are like rules for what kinds of paintings are allowed. But the arrow of time is like the direction the artist happens to be painting. It comes from how the painting started, not from the canvas or the rules. Now, I want to tell you about something even stranger. Why do we remember the past but not the future? You might think this is obvious. The past has happened and the future hasn't. But wait a minute. In the block universe picture that comes from relativity, the future is just as real as the past. It's all there, laid out in four-dimensional space-time. So why can we only remember one direction? Here's what I realized. Memory is a physical process. When you remember something, there's a record of it in your brain, encoded in the connections between neurons. That record is a low-entropy structure that was created by the event you're remembering. The reason you remember the past and not the future is the same reason the egg breaks and doesn't unbreak: entropy. Let me explain. When you see something happen, light from that event enters your eyes, triggers neurons, and creates a memory trace in your brain. That whole process increases entropy. The creation of a memory is an irreversible thermodynamic process. You can't uncreate a memory the same way you can't unbreak an egg. So memories point in the direction of increasing entropy, which we call the past. But here's the beautiful part. This means that the psychological arrow of time, our sense that the past is fixed and the future is open, is not fundamental. It's a consequence of thermodynamics. It's a consequence of the fact that the universe started in a low entropy state. If somehow you could have a creature that existed in a region of decreasing entropy, it would remember the future and anticipate the past. Its experience of time would be reversed. Now, you might say, well, that's very nice, but what does it mean for causation? We all have this strong intuition that causes precede effects. I throw a rock at a window, and the window breaks. The throwing causes the breaking, not the other way around. But is this built into the laws of physics? It is not. The fundamental laws don't distinguish between cause and effect. They just describe correlations between events at different times. If I told you the complete state of the universe at any moment, the laws would tell you what happens at all other moments, past and future equally. There's no causation in the fundamental physics. There's just evolution according to the laws. So where does our sense of causation come from? Again, entropy. We say the throw causes the break because the throw is in the lower entropy direction and the break is in the higher entropy direction. Causes are in the past, effects are in the future, because that's the direction entropy increases. Our whole concept of causation is a macroscopic, thermodynamic concept, not a fundamental one. This has deep implications. It means our intuition about cause and effect, about past and future, about the flow of time, all of it arises from a very special fact about the early universe. The low entropy initial condition is doing an enormous amount of work. Without it, there would be no arrow of time, no memories, no sense of causation, no life. And here's what really gets me. We don't know why the universe started in a low entropy state. The laws of physics don't require it. In fact, a low entropy initial condition is incredibly unlikely, precisely because there are so few such configurations compared to high entropy ones. So why did the universe begin in this special way? Some people think there might be a deeper principle we haven't discovered yet. Some think it has to do with cosmological theories about the multiverse or the very origin of space-time. I don't know. Nobody knows. But I find it wonderful that this simple question, why does time have a direction, leads you straight to the deepest mysteries about the origin of the universe. So here's what I want you to take away from all this. Time is not a river that flows. It's not a universal background against which things happen. It's a dimension that's woven together with space. The apparent flow of time, the arrow pointing from past to future, is not built into the fundamental laws. It emerges from the improbable initial conditions of the universe. Your memories, your sense that the past is fixed and the future is open, your belief that causes precede effects, all of these are consequences of entropy. They feel fundamental, but they're not. They're emergent. They arise from the statistical behavior of vast numbers of particles moving from unlikely configurations toward more likely ones. The universe is not what it seems. Time is not what it seems. And the more you understand physics, the more you realize that our everyday intuitions, however useful they are for getting through life, are just approximations. The real world underneath is much stranger and more beautiful than we ever imagined. What I love about physics is that you can start with a simple question like, why does an egg break but not unbreak? And you end up confronting the deepest mysteries of existence. The question of time leads you to entropy, which leads you to the initial conditions of the universe, which leads you to ask why the universe exists at all and why it has the properties it does. And the honest answer is, we don't fully know. We have pieces of the puzzle, beautiful pieces, but the complete picture is still hidden. That's what makes it exciting. There's still so much to figure out. And maybe, just maybe, somebody watching this right now will be the one to crack it. You just have to start asking questions and not be satisfied with easy answers. Nature doesn't care about our intuitions. Nature cares about what's true. And finding out what's true, even when it destroys everything you thought you knew, that's the joy of it. That's what time really is. Not a flow, not a dimension like space. It's an arrow that emerges from probability, from the strange, improbable beginning of everything. And every second you experience, every memory you form, every cause and effect you observe, is a ripple from that beginning, spreading out through the universe, like cream spreading through coffee, moving always, inevitably, toward greater and greater disorder. That's time. That's the deep, strange, beautiful truth about the thing you look at on your wrist every day without really thinking about what it means.